Today I'm going to explain you an essential data structure in computer science, the linked list. But don't worry, I'm going to make it super simple to understand. We are going to cover what is a linked list, a real-world analogy, how memory and pointers work, different types of linked lists, how to implement a linked list in C++. By the end of this video, you'll not only understand linked lists, but also be able to implement one yourself in C++. So let's jump right in. First off, what exactly is a linked list? According to Wikipedia, in computer science, a linked list is a linear collection of data elements whose order is not given by their physical placement in memory. Instead, each element points to the next. It is a data structure consisting of a collection of nodes which together represent a sequence. In its most basic form, each node contains data and a reference, in other words a link to the next node in the sequence. Imagine you own a small business. In your company, there's a CEO. Directly under the CEO, there is the CTO. The CTO oversees the team. That team has a project manager in charge. The project manager has a lead engineer working under them, and the lead engineer supervises the developer. Now let's say you want to change something about your project. You don't need to have a meeting with the developer of the project. Instead, you simply talk to the CEO, then the CEO will have a meeting with the CTO. The CTO will then communicate with the project manager, who will talk to the lead engineer, and finally, the lead engineer will inform the developer. In this way, your relationship is directly with the CEO, and the CEO's relationship is directly with the CTO. The CEO might not even know all the employees working on the project. This structure is similar to a linked list in programming. Let me explain. In a linked list, each element, like an employee, points to the next element. You can make changes by talking to the first element, which is the head, and it will communicate down the line to others without you needing to interact with every single part directly. Now let's see some properties of linked lists. A linked list has the following properties. Each element is connected by pointers, which I have talked about earlier. The last element points to null. Linked lists can grow or shrink in size during execution of a program. Can be made just as long as required until system memory exhausts. Does not waste memory space but takes some extra memory for pointers. It allocates memory as the list grows. Wait, takes some extra memory for pointers? We should know how computer memory works before we understand the concept of linked list. I'm giving you a simple explanation of how memory works. Later, probably I'll make another video that goes into more detail. I'll drop some link in the description below for more information on how memory works. But for now, let me demonstrate how memory works. In computer memory, there are two key features: address and value. Every piece of data is stored at a specific address, and that address can be used to access the data. This concept is crucial for understanding how linked lists work. Let's delve into the specifics of how addresses and values are managed in a linked list. Each node in a linked list contains data, the actual value or values stored in the node, and pointer, the address of the next node in the list, or it could be null if it is the last node. When you create a linked list, the nodes are allocated in heap memory. Heap memory is a region of computer's memory used for dynamic memory allocation. Unlike stack memory, which is managed automatically and operates in last-in first-out manner, heap memory allows for more flexible and complex memory management. Suppose you're creating a node, which we'll call node 1 to make it easier to understand. We'll name it node 1 because it is the first node in the linked list. First, you need to allocate memory for node 1. Then set the data value, let's say 5, if the node you created is the last element, or if there's no node after your created node, then its next element will be null. In our case, since this is our first node, the next element will be null because there's no node after it. Suppose node 1's value is stored at address 0x1000 and the pointer to the next node is null, which is stored at 0x1008. When you create another node, you need to allocate memory for node 2. Let's say node 2's value is 10 and its pointer is null, which is stored at a new address. Now because it's a linked list, we have to link the previous node, which is node 1, with the newly created node 2. We do this by updating node 1's pointer to store the address of node 2. Now, let's say you want to find the next value after 5. The program can look into the memory address stored in node 1's pointer. It will find the address of node 2 and can immediately access node 2's value, which is 10. By updating the pointer in node 1, you create a link to node 2, forming a chain that is the essence of linked lists. There are many different types of linked lists. However, understanding the four main types will give you a solid foundation, which are singly linked list, doubly linked list, circular linked list, and circular doubly linked list. In a singly linked list, each element contains a data element and a reference to the next node in the sequence. Traversal is possible only in one direction, from the head or start of the list to the tail. The last node's next pointer typically points to null to indicate the end of the list. In a doubly linked list, each node contains a data element and a reference to both the next and previous nodes in the sequence. Traversal can occur in both forward and backward directions, allowing for more efficient operations such as deletion from the end of the list. Doubly linked lists require more memory per node due to the additional pointers. The last node's next pointer points back to the first node, forming a circular structure. There is no end of the list in the traditional sense, as traversal can cycle continuously through the list. Traversal can start from any node in the list and continue until the starting node is encountered again. Similar to a linked list, the last node's next pointer points back to the first node, forming a circular structure. Like a doubly linked list, traversal can occur in both forward and backward directions. Each node contains pointers to both the next and previous nodes, allowing for efficient traversal in both directions. We already know how linked lists work, and generally linked list means a singly linked list. This list consists of a number of nodes, in which each node has a next pointer to the following element. The pointer in the last node is set to null. I'll be explaining this using C++. C++ is a great choice because it strikes a balance between low-level programming and high-level programming, making it accessible to enthusiasts of both types. And I'll share a GitHub link where you can find linked list implementations in 5 different languages. Let's dive into the code. First, we create a node class. Each node in a linked list stores data and a pointer to the next node. This is the basic building block of our linked list. Let's write the code step by step. Here, we define a node class with 2 public members. Data, this will store the value of the node, and next, this is a pointer to the next node in the list. Now let's add a constructor to initialize these members. In the constructor, we initialize data with the value passed to the constructor. We also set next to null ptr, indicating that the new node does not point to any other node yet. Next, we'll create a linked list class to manage these nodes. In the linked list class, we have one public member, which is head. This is a pointer to the first node in the list. Now let's add a constructor to initialize the head. So initialize this head to null, meaning the list is empty initially. If the list is empty, head will be null. So let's take a moment to review what we have done so far. We created a node class to represent each element in the linked list and a linked list class to manage these nodes. The node class has a data member to store node's value and a next pointer to point to the next node. The linked list class has a head pointer to track the first node in the list, which is initialized to null, indicating an empty list. Next, we'll write function to add nodes to our linked list. The insert head method inserts a new node at the start of the list. Here's how it works. We first create a new node by calling new node. When you call new node, it performs several actions. The new operator allocates memory for a node object from the heap. The size of the memory allocated is sufficient to hold the node object. After allocating the memory, the constructor node is called. This initializes the node object. Specifically, it sets the data member variable to the value passed, in this case data, and initializes the next pointer to null. The new operator returns the pointer to the newly allocated and initialized node object. This pointer is then assigned to new node. Let's break down the code line by line with this in mind. New node allocates memory for a new node object on the heap. The constructor node is called with the value data. The result is a new node object with the data set to the first value and next set to null. Then the new operator returns the address of this newly created node object, which is then assigned to the pointer new node. For updating the next pointer, this line sets the next pointer of the new node to the current head of the linked list. This links the new node to the existing list. It means if there are already some nodes in the list, then there must be a head. So the next pointer will be the old head, or if there's no node in the list, then we already initialize the head as null, so the new node next will be null. So this way this function inserts the node at the beginning of the linked list. Finally, this line updates the head of the linked list to point to the new node. This makes the new node the first node in the list. Let's now create another function which will insert the value at the end of the list. The inserted in functions add a new node at the end of the list. Let's break down how it works. We first create a new node with the given data. The new node's next pointer is set to null because it will be the last node in the list. If the head is null, it means the list is currently empty. In this case, we simply set the head to point to the new node, traverse to the end of the list. If the list is not empty, we start from the head and move through the list node by node using a while loop. We keep moving until we find the last node, the node whose next pointer is null. Once we find the last node, we update its next pointer to point the new node. This way, the new node is successfully added at the end of the list. Now let's create a delete functions which will remove the node from the list. The delete node methods removes the node that matches the given data. First, we check if the list is empty by checking if head is null. If it is, the function returns immediately and there's nothing to delete. Next, we check if the head node contains the data to be deleted. If the head node contains the data, we store the head node in a temporary variable, update the head to point to the next node, and then delete the old head node to free the memory. If the data is not in the head node, we start traversing the list from the head. We move through the list until we find the node whose next node contains the data or until we reach the end of the list. If we find the node with the given data, we store the node to be deleted in a temporary variable, update the next pointer of the current node to skip the node to be deleted, and then delete the node to free the memory. This method ensures that the node with the given data is removed from the list while maintaining the integrity of the list structure. Finally, the printlist method traverses the list and prints the data of each node. Let's put everything together in the main functions. In the main functions, we created the linked list object and perform various operations like inserting and deleting nodes. And finally, we print the list and see the result. That's it for today's tutorial on linked lists. Thanks so much for sticking with me till the end. If you enjoyed this video or even if you have some constructive feedback, please leave a comment below. Your feedback will help me make better videos for you. Thank you for watching and supporting my journey. See you in the next one.